Okay, going full screen. All right, someone tell me something that their group noticed. What did you notice?
Negative slope.
Negative slope, is that what you said? Fantastic. What else? Put the phone away, please.
I'm writing down my homework.
Oh, okay, that's fair. All right, what else? People like cheap haircuts. How did you know that people like cheap haircuts based on this? Uh-huh. Ah, okay, did you guys hear that? The cheaper the price would be to the left, and then we have more customers, right? When we have a cheaper price. When we don't charge anything, we get a whole bunch of customers, right? Okay. So what else? Did anyone else notice anything? Okay, more expensive. There's some sort of some price of a haircut where they end up getting no customers, right? What do you wonder? Yeah.
Why is it a straight line?
Why is it a straight line? That's a good question.
Does that mean their profit's the same still?
Good question. So no, because we have a higher price, we have less customers, but we don't know like which product of price times customers would be the highest. It doesn't mean that their product stays the same all the way through. Yes?
Why do they use this type of graph?
Okay, again, yes. Why is it linear, right? Okay. Does anyone wonder what that price is that causes them to have no customers?
So, obviously a high price. $50.
$50? $10?
How do you no,
Yeah, I think so. Anyone wonder what their maximum profit is, right? What price gives them the highest profit? So here, obviously, they're not making a profit because they're charging zero, even though they have the most customers, so they're not making anything, right? Here, they're charging a whole bunch, but here they have a whole bunch of customers. Here, they're charging a whole bunch, but they have no customers, so they're making zero. So where do you think the highest profit occurs?
Middle.
Somewhere roughly in the middle. Yeah, it's a good guess. Okay. All right. What kind of a function is this?
Linear.
How do you know it's linear? Because it's a line. Very good. Today we're doing 2 sections in one day. We're doing 3.1 and 3.2. 3.1 is kind of an introductory section getting us used to different types of graphs. 3.2, we're going to jump into function notation, which is like one of my favorite things. Chapter 3 is all about functions. When you finish chapter 3, you should have a fairly decent understanding and knowledge of a good variety of different types of functions. Not all the different types of functions that are out there, but a good number of them. We're gonna touch on quite a few different types of functions in this chapter and get you exposed to what they look like and what their graphs look like and everything like that. So 3.1 and 3.2. All right. Noah, are you ready in the back? Are you ready? Okay. Ronan, you ready over there? Yes. Everyone all of a sudden is thirsty. All right. Linear functions. Linear functions are functions that increase or decrease at what your book calls a steady rate, which I don't like the word steady, but I get it. It's kind of a nice descriptive word. I like to think of it as a constant rate. When I say rate or rate of change, what does that make you think of? What word? Slope, right? It's written on the board. So a linear function is a function that has a constant slope, a constant rate of change. Any function that is increasing means that the function goes up from left to right. We always read functions from left to right. Just it's the same as how we read a book, right? So from left to right. So if the function is going up from left to right, it's called increasing. And if the function is going down from left to right, it's called decreasing. What do you know about the slope if your function's increasing? It's positive. What about if it's decreasing? Negative. That's called the pinned principle. Positive increasing, negative decreasing. Okay, any questions on this slide? Not much to it. We're about to jump into a problem. Now, this problem right here, this function is not linear, but it is a whole bunch of linear functions put together. So what do we call that? We actually call that a piecewise linear function, which we'll learn about piecewise functions later on. But a piecewise function means you kind of pieced together a whole bunch of different functions. So we have all these different lines, and they all have different equations, but we want segments of them put all on one big giant graph. So this is called a piecewise linear function. It's all linear if you break it into pieces. Okay, so students at Central High School are complaining that the juice vending machine is frequently empty. Student council members decide to study this problem. They record the number of cans in the machine at various times during a typical school day and make a graph. Based on the graph, at what times is the juice consumed most rapidly? When is the machine refilled? How can you tell? When is the machine empty? How can you tell? What do you think the student council will recommend to solve the problem? In your groups, I want you, we're not going to put this on whiteboards. We did last hour, but we're not on this hour. We're going to do something different this hour. So I want you to take a couple minutes, discuss all four, and see if you can come up with answers to all four. And then we're going to verbally walk through this, and then we'll do a whiteboard activity. Thanks. So when is the juice consumed, meaning purchased, the most rapidly?
Before school.
10:30 to 12?
At school then. 30 to 12.
11:30 to 12:30?
3:30. Oh, no. No.
When we say consumed or purchased, will the graph will be increasing or decreasing?
Decreasing.
It will be decreasing. And most rapidly, no, that's good. Very good. That means the line's gonna be really steep, right? Okay, so we have a really steep decreasing line. Several of you said from 11:30 to 12:30, right? And then there's one other time we've got a really steep decreasing line.
4 to 4:30.
3 to 3:30?
Yeah.
Yeah, 3 to 3:30. So what do you think's going on from 11:30 to 12:30? Lunch. What do you think's going on from 3? It's after school, right? People apparently want juice on their way out. Okay. And then it's also decreasing from like 4:30 to 7. It's like after school activities, right? But it's not decreasing as rapidly. Does that make sense? Okay. All right. Okay, good. When is the machine refilled? Tell me the times just tell me the start times of when it's refilled. 10:30, 4, 12:30, and sometime in the night. Yes, very good. So, how do you know that it's being refilled? Because the graph's going up, right? The only way for the number of cans in the machine to increase is if someone is refilling the machine. It's not like they're reproducing, right? So the only way for the number of cans to increase is if someone's refilling the machine. So 10:30, 12:30, and 4 look like the 3 times that it's being refilled. But as Avi pointed out, look, we end down here, but we start the day up here, which means sometime in between there they had to show up and refill again, right? Which is really, I thought that was very astute. Okay, when is the machine empty? 12:30 and 3:30 to 4. It's sitting there empty, right? Okay, so the complaint is the empty times. So is there something that we could do to help? Yes, Isaac. Okay, buy more vending machines. That's fair. Okay, yes, moving. Refill a little bit earlier, right? So if we refill, like we said was around 12. So if we refilled, here, right, then maybe it wouldn't drop to empty, so quickly. Okay, and then maybe refill early again, like here, so that it would, we'd be ready for the lunch rush and the afternoon rush or whatever. Refill a little bit earlier. Any other ideas? Yeah. Refill every hour, right? Refill every hour in the hour. This is a lot of that, I know. You'd have to have a vendor just pretty much on staff, right? So, yeah. Okay. All right, good. Does everyone understand how we came up with those answers? Talk to me if there are any questions. Everyone was able to kind of read and interpret? Yeah? Okay. All right, the next thing we're going to talk about are graphs that are not linear, graphs that are curvy. So when you have a graph that is curvy, any curvy graph is made up of these 4 shapes. No matter how you draw your curve, every single curve can be broken down into these 4 shapes. So for example, this top shape, that's right here, and then it kind of shows up again right there, right? And then the second shape, and I just kind of winged this. Let me make that top, this one a little bit longer, right? And then maybe a little bit like right here, right? And then this third shape, let's see. I see it kind of right here, kind of right there. And then this fourth shape would be like here and here, these blue spots right there. So every single curve that you ever see graphed is made up of 4 different curves kind of pieced together. Now, these 4 different curves have different descriptions. The first 2 are both similar in that they are both what? Increasing. They're both going up from left to right. But do they look exactly the same?
No.
No. If you were to look at those 2 curves and say I said that those curves describe your salary increases over the span of your life, which one would you want to have? Probably the second one, right? Depending on time. But yeah, probably the second one, because you're going to hit a much higher salary much faster. This guy, you're going to hit some kind of a cap and just kind of level off, right? This one's more like a teacher salary. So anyway, but this one, it's true. It's not a dig. There's a cap. You hit a certain number of years and then you just stay the same, right? So anyway, these guys, this might be, you're in business and you just keep going up. So maybe you're, whatever. All right. So anyway, so how do we describe this? This is increasing, but it's slowing down. Slowing down. This guy's increasing and it's speeding up. Woo. When you increase but you're slowing down, what ends up happening is your slopes actually get smaller. So even though the slopes are all positive, they're getting smaller. Does that make sense? So like you might have a slope of 100 over here, but then over here you might have a slope of 1/2, right? Here, your slopes kind of start small and then your slopes get bigger. Both of these have positive slopes, but one is slowing down and one is speeding up. The bottom 2 graphs are both what? Decreasing. Now this one is slowing down and this one is speeding up for decreasing purposes, right? So we're slowing down, we're speeding up. Now, technically, even though we're slowing down, the slopes are technically getting bigger. I know it's weird, but because they're negative, this one's like -100 and this one's -1/2, which is a bigger number. So we're not really talking about the numeric value. We're talking more about like the the size of the slope, like the magnitude, the absolute value of the slope. So really steep, shallow. If you're going from steep to shallow, you're decreasing, but you're slowing down. If you're going from shallow to steep, you're decreasing, but you're speeding up. Now, I taught third period some additional vocabulary to go with these curves, but I don't know if I want to teach it or not. It will never show up on a test or a quiz or anything. I'm going to show you real quick. You don't have to write this down. So if you don't want to learn this, just like close your eyes for a minute. So whenever you have a shape that is either this guy right here, which is this one, or this part right here, which is this one. So if you take these two shapes, the two middle ones, and put them together, you get this guy. You take the two top and bottom shapes, you get this guy. This type of shape is called concave up. This type of shape, concave down. When we're talking about functions, there's no such thing as convex. You're concave up or you're concave down. So I like to say up like a cup, down like a frown. But a lot of people like to say up like a smile, down like a frown. I just like cup because it rhymes. But, you know, up like a smile, down like a frown. So concave up, concave down. It's just describing if your shape is like this or your shape is like this. So you can be increasing concave up or increasing concave down. Just depends on your shape. So later on, when you get a little older, you will have to use calculus to determine what shape your function is, and then you're going to have to graph it from scratch without, you know, knowing any points or anything. But it's really fun. I like doing it. Okay, does anyone need any more time on the screen? Okay. On your whiteboards, I want each group first to take 10, maybe 15 seconds, discuss what shape this graph would be, and then send one member up to your whiteboard to give you a quick sketch of what you think this graph will look like. We're talking about if you take a cup of cocoa, you heat it up in the microwave, and then you take it out and set it on the counter. What is happening to the temperature? All right? Okay, go ahead. That's great. Ruben, that's great. Okay, there we go.
They first cool down rapidly and so they level out. You have to label it.
Do what you think. No. You're asking if we have to label it? I'm saying you make the call.
I have to label it.
Dare to be different. I like it.
It's not going off. It's decreasing.
All right. All right, the two things we're talking about here are time and temperature. So what were you thinking would be a good thing to put on the x-axis? Time. Okay, so as time goes by, what's happening with the temperature, right? Whoa, okay. We have a lot of almost everyone has the same answer except one group that dared to be different. And I like the different interpretations. Do you want to explain why you came up with, or how you came up with that?
Because so when you take something out of the microwave, it stays out like a constant amount
temperature and slowly decrease it. It doesn't just like go from like 100 degrees to like 5, in like 1 minute. It like stays like that for a while, but then eventually it'll reach room temperature and it'll stay like flat. That's what it looks like that.
Okay. Are you sure of that, or is that kind of your assessment of this, like your personal
Well, that's
thinking?
how it is in biology, like science.
Really? Okay.
It's like the
Okay. So in order, I love that you're connecting it to science. I'm going to connect it to science as well. So there is a concept called Newton's law of cooling. Have you learned of Newton's law of cooling yet? Okay. So don't feel bad. This is great. I love that you're thinking out the sidebox, the outside of the box, and I love that you weren't afraid to be different and stand up for what you thought it was. Right? That's fantastic. I applaud that. Right? So well done. And to me, again, I say it too often, but that's what makes you a mathematician. Right? Okay. So willing to take a risk, right? So anyway, very good. So actually it is going to go like this. And it's okay. The most dramatic temperature increase happens from the moment you take it out of the microwave. So you take it out of the microwave and you set it down and it immediately starts trying to hit that room temperature. So it's going to drop the most dramatically during the first few minutes of time. And then as it gets closer to room temperature, it's actually going to decrease at a slower and slower rate. So what ends up happening is that rate is proportional to the difference between the temperature of the cocoa and room temperature. So if the difference is big, the rate is big. If the difference is small, the rate becomes small. So the bigger the difference, the faster the rate. That is what Isaac Newton came up with. Okay, so good discussion. Moving on. All right, in your groups, what we are doing here is we have 3 vases. We are filling each of the vases with water, whatever, liquid of some sort, right? Okay, your job is to decide which graph goes with which vase. Now, what I would like is for a different person from each group to go up to your board, label A, B, and C, and then next to A, B, and C, label 1 or 2 or 3, all right? But first I want you to discuss it. Then go up to your board.
No, I'm going to answer.
Yeah, A is 3.
So every single group in the classroom got the exact same answer. Let's just take a look for letter A. Which graph does it go with? 3. How do you know?
It's the same.
Constant rate, right? It's just always going up at the exact same rate because there's no change in the width of the bottle or whatever. Yeah. So this goes with graph 3. All right, the next 2 took probably a little bit more discussion. So everyone said that B goes with graph 1. Does anyone want to explain why? Yeah, B.
So the bottle, it has like that curved thing at the bottom.
Yeah.
And so and then it gets thinner, so which means it doesn't go in a straight line, except it does a weird funky curve.
Weird, funky curve. Yes. So I'm going to break it down even more. So everything you said was absolutely right. Take a close look at this curve. See how the beginning looks like that? So do you remember how we described that as even though it's increasing, it's slowing down? Does it make sense for like this part of the bottle that even though the amount of water is increasing, it's slowing down because the bottle's getting wider and wider, right? And then as the bottle starts to narrow, then we start speeding up. Does that make sense? Okay. All right, good. So let me use this slide. Oh, what did I just do? There we go. Okay, so this would be graph 1, and then by default, this one is graph 2, which is just always increasing at an. By the way, when we say increasing and speeding up, we can also say this kind of fancy expression, increasing at an increasing rate, meaning that we're increasing and we're increasing faster and faster and faster, right? So we're always increasing. The amount of water is always getting higher, but not only is it getting higher, but as you move up, it's getting higher faster, right? Okay. All right, we're going to talk about functions now. We're moving into section 3.2. So when we talk about functions, so far, everything that we've been doing has been what's called a relation, although most of them are functions too. Oh, good. Marcus, you got that fast. That's good. All right. So a relation is just any type of an equation that relates to things. So it can have, usually it's x's and y's, and they're related to each other somehow. A function is also a relation, but a function is special. What makes a function special, and the reason these are important, is they're so important in applications. So without functions, there's so many things we wouldn't be able to do. So functions are really like one of the most important concepts in all of math. So it's a special type of relation where for each input, there is at most one output. For each input, there is at most one output. Now, this definition up here says for every value of the independent variable. Whenever you see independent variable, that means input. And the most common letter we use for that is X. Then it says there is at most one value of the dependent variable. The dependent variable is your output, and we usually call that Y. So how do we know if a relation is a function? So if we have a graph, it's easy to test because the graph has to pass what's called the vertical line test. How many of you have heard of vertical line test before? Oh, good. Fantastic. Okay. So vertical line test says that if you kind of move a vertical line along your function, if it never passes through more than one point at a time, then it's a function and it passes the vertical line test. But if there is a spot where a vertical line passes through more than one point, then it is not a function. Now, it doesn't have to be everywhere. So, for example, if I have this graph right here, this passes the vertical line test all along here and all this way forever. But it fails it for this little section here. It's 3 points or 3 values right there, right? If anywhere on the graph it fails the vertical line test, then that graph is not a function. Anywhere, if even one time it fails the test, it is not a function. Okay, so those of you who have not heard of vertical line tests before, do you kind of understand what it means? So if a vertical line only ever passes through at most one point, then your graph is a function. If it ever passes through more than one point, not a function. Okay. All good. Usher, you need another minute to write? It's okay. I'm thirsty too. I forgot to grab my tea before coming in here today. Okay. All good? Yes? Good. All right, so here's what I want you to do. In your groups, just at your desks, I want you to look at each of these. We have 3 graphs. Right, 3 graphs. And then we have 3 of these like kind of funky little drawings that indicate relations between X and Y. I want you to decide for all 6 of these, just think yes or no. Yes, this is a function, or no, it's not a function. So I'm going to give you a minute to discuss in your groups for each. All right, let's just do the top 3 first because I think we'll all agree on them. This first graph, yes or no?
Yes.
Yes, this is a function. Whoop. Yes, this is a function. What about this graph?
No.
No. Fails the vertical line test anywhere in here. So this would be a no. What about this set of dots? Yes. Always passes the vertical line test. It's a function. All right. Now let's go down here. I don't think there's any argument on this first one. Is this a function?
No.
Yeah.
Yes.
Yes. Yes, it is.
Yes.
Yes.
No. Yes.
Yes.
Horizontal. Yes.
It's a horizontal.
It's horizontal.
Okay. So I love that this group is saying horizontal. I'm going to just take 2 seconds and sketch a little graph. If x is 1, y is 2. If x is 2, y is 2. If x is 3, y is 2. If x is 4, y is 2. Is this a function?
Yes.
Yes. It's okay to have every single x value pointing to the same y. That's okay. That creates the horizontal, right? So well done, you guys, in figuring this out. So this is a yes.
I
bring this down so I don't get confused.
X cannot equal 2.
All right, what about this last one?
No.
No. If we were to sketch a graph of this guy, we'd have 1, 1, and 1, 3. We'd have 3, 2, and 3, 4, right? We would fail the vertical line test twice. So, oops, I covered my no. Oh. So, as soon as you have an x pointing to more than one y, not a function.
Yes.
Little tricky. It's easy to get them mixed up. If you ever get them mixed up, just take a set. It doesn't have, it's not like you have to pull out graph paper, right? Just give yourself a tiny rough sketch of the dots and just take a look, right? All you have to do is sketch 2 or 3 dots and you'll know. So, yeah. Just stretching? Okay. All right. So, we're going to put another thing on whiteboards, but how did my Y end up transferring over to this? There we go. Okay. So, what I want you to do is see if your group can decide on what a graph of this looks like. Send up yet another person unless you're, yes. Okay, so hang on. So we have the price of candy goes up $2 every day. The price depends on the amount of days the candy has been for sale. The original cost is $1.50. All right, so I give you about a minute to discuss what you think this graph looks like and draw it on your. Hey, what kind of a graph is this going to be? Linear. How do you know it's linear?
Arithmetic.
Because it's an arithmetic sequence. Look at you relating old topics to new topics, right? Okay, so yes, it's arithmetic. So I gotta be honest, when I did this, I put $1.50 on my y-axis. So I had what would we label the x-axis? What does this represent? Days. And then what would the y-axis represent? Price. So I put $1.50 and then drew a line going up from there. There were some groups who started their line after the y-axis and said, hey, we're not starting on day 0, we're starting on day 1, right? Most of the time we say day 0 is our starting, and then each day after that, like 1 would be after 1 day, 2 would be after 2 days, and so forth. But you could make an argument the other way, right? So I get it. Before I sketch the line, we have, what's the slope?
2. Just
So-
two.
Is it 2?
It is 2.
Are you sure?
Yeah.
Mike, put the phone away. Okay, so with a slope of 2, is our graph going to look flat like this?
No.
Is it going to look kind of shallow like this?
No.
Is it going to be one of these like 45-degree angle, even Steven kind of lines?
No.
Is it going to be slightly steeper?
Slightly steep.
Slightly steeper, right? Any slope that's, what is that, what's the slope if you're a 45-degree
One.
angle, even
One.
Steven? Slope is 1, right? Okay, so 2 means slightly steeper, whatever you want to interpret that to be. All right, fantastic. Moving right along. Okay, now we're getting into function notation. We have this G and the number 1 next to it. If I were to speak this expression in words, does anyone know what I would say?
G of 1. G of 1.
G of 1. Very good. I say G of 1. Now, guys, if you have not been paying attention or didn't need to, now I really want you to pay attention because this stuff is going to last. You're going to be doing this through college. So make sure you kind of learn this. G of 1. This is not G times 1. Parentheses usually imply multiplication, but not with functions. So with function, when you're talking about the name of the function, then it's not the letter times the thing next to it. That whole thing is the name. So in this case, this is G of 1. Now, this 1 that's inside of these parentheses, is that going to be an x value or a y value?
X value. And an X value.
It's an input. We're plugging 1 into the G function. It's an x value. So this 1, that's an x value. It's input. Now, so 1 is an x value, but G of 1 is not an x value. What's G of 1?
3.
It's a y value, and specifically it's 3, right? How did you know it was 3?
I just looked.
You just looked?
Yeah.
Where?
The graph. The graph.
On the graph?
1.
1.
And we have the point 1, 3. So when x is 1, G of 1 is 3, your y is 3. So this is your y value. It's your output. All right, everyone in your groups, just take a second and discuss what's G of negative 2.
Settle. No.
Okay, does everyone agree? What is it?
0.
0. Good, because of the point negative 2, 0, right? Does everyone understand when x is negative 2, G of negative 2 is 0. Okay. All right, now this 0, find x when G of x equals 0. This 0, is this an x value or a y value? Y value. So we want to know what x has 0 as a y value.
Negative 2.
You just found it. It's negative 2. Are you all with me?
Yes.
Last one. Take 10 seconds in your groups. Find x when G of x equals 2.
2. 2. 0 and 2. 0 and 2.
Yeah.
0. Oh. 0, 2.
All right. What did we find? 0
And 2.
and 2. Can there be more than one x value with the same y value?
Yeah. Yeah.
Yes. What there can't be is more than one y value with the same x value. It gets so confusing. But just look, it passes the vertical line test, right? But we have a point when x is 0, y is 2, and when x is 2, y is 2. So we have 2 answers for this one, right? Find x when G of x is 2, when x is 0, and when x is 2. Does everyone see that? Ashwin, I can't tell. Okay, let's make sure you what?
How'd you find
So this 2 right here, that's a y value, right? So we want to know what x values have a y value of 2. If you were to write ordered pairs, what would this ordered pair be? 0, 2, right? So the x value of 0 has a y value of 2. If I were to write this as an ordered pair, what would this one be? Right? We're looking for what x's have a y value of 2. If you were to list off all the ordered pairs, those are the 2 where the y value is 2. Did that help? Okay. Now, do you all understand the notation? Like, if I said, hey, what's g of -1? What would you tell me? Do you understand why? I'm just talking to Ashwin right now. Okay, what is this? Is this an x or that's an x? Go on your graph to where x is -1. What's the y value? Do you see it? Okay, stop yelling out answers, guys. Okay, Ashwin and only
I get it.
Ashwin. Okay, do you get it? Okay, all right. So, just wanted to quote my cousin Vinny for those of you who have seen it. All right, good. Any questions on this? We're not done. I'm just making sure. Okay, so now we're going to deal with function notation without a graph.
Oh, nice. You plug it in.
Okay.
Plug it in.
Yes. Now, I love using the words plug it in. Technically, it's not mathematically the right way to say it. What we're supposed to say is we substitute.
Oh.
We substitute this number for the x value in our function. But you will hear me say plug it in all the time. So anyway, okay. So if f of x equals 2x minus 5 over x minus 3, and we want f of 8, what? Shh. Hey, is this 8? Is that x or y? X. Your input is what you're plugging into your function. This is an x value. You replace all your x's with 8s. Replace all your x's with 8s. And then simplify. So go ahead and take a second. Replace all your x's with 8s and see what happens.
Was this something you said 0?
No, not really.
Wait, what's the difference between 2 and x?
Oh, that's a good question. I will tell you when, like, in just a second.
Isn't it the same? It's just
Very
it's the same like a variable.
Yeah.
Yeah.
Sounds like we're done. Is everyone done? No, wait, Tori's still working. Oh, okay. All right, let me gather you back. 2 times 8 minus 5 over 8 minus 3. Does everyone understand what we did here? And I'm looking at all of you. Okay, Joe, you good?
Yeah.
Yeah? What am I going to do to simplify? What should I do first? What is it?
16.
Very good. All right, what's 16 minus 5? 11. What's 8 minus 3? 5. Can I reduce 11 fifths?
I mean,
Nope, then I'm done. Do not write mixed numerals. Just leave it 11 fifths. All right. I can't move this here. Okay, now we're going to do the same thing with -7. So you're going to do the exact same thing. Replace your x's with -7s, and then simplify. Take a second and do that. 2 times negative 7? Hey, what's negative 14 minus 5?
Negative 19.
What's negative 7 minus 3?
Negative 10.
What's negative 19 over negative 10?
19 over 10.
19. Yes. Now, I have a couple things to mention to you. So there was a question, what's the difference between f of x and g of x? There's no mathematical difference except that sometimes we want to give functions different names. It's like if I have multiple children, I might call one Fred and the other George, F and G, right? So just to differentiate between them, right? It makes me think of George Foreman, who named all his kids George, right? But normally we have different names for different functions, and in just a second we're going to see problems where one problem might have several different functions in it, so they each need their own name, so you can tell them apart, right? Now, I want to make sure you understand something. The question came up in third, and I hadn't thought of it, and I was so glad the student asked it, because I want to make sure we're really golden crystal clear on something. When I have f of 8 equals this, right? So I had a student who did all of that perfectly, had f of 8 equals 11 fifths, and then divided by 8, right? And said that f was 11 40ths. You can't divide by this. It's not f times 8. This is f of 8. These two things are, they're married, like they're connected. They cannot be broken apart, right? So it's not f times 8, it's f of 8. Now, here's the other thing. If I call the function f of x, I don't have to have the of x part. I can just call it f. The of x is actually a courtesy to tell the reader what the input variable is. But you don't have to have it. You can just call it f. You can call it g. You can call it the word Fred, right? So you can call it whatever you want. But because we're plugging stuff in here, then we put the of x so that people know what do we substitute the 8 for? We substitute the 8 for x, right? Okay. But just know that of x, oh, and something else someone in third period said, and I really loved it, and I want to make sure you understand something. F of x is the same, I'm going to write it with words. F of x is the same thing as if I were to call this y. If I had y equals 2x minus 5 over x minus 3, it'd be the exact same thing. The only difference is that f of x is in function notation. Here's y. In function notation. So it really just tells us, hey, this is a function, right? So anyway, so if I called this y equals this stuff, or f of x equals this stuff, they're the same thing. It's just that f of x is in function notation. Okay, let's move on, because we only have like 8 minutes left. Okay, algebra with functions. So f of x is 2x plus 1. G of x is x minus 3. Part A, find f plus g of x. I want you in your groups. I'm going to give you 15 seconds to take a guess at what f plus g of x is. Go.
3x minus 2.
Yeah, the answers of those two functions plus each other.
Yeah, so
3x.
no, 3x
Minus
minus 2. We need an x. Except it's like x.
Well, no, she was just asking.
I know.
Okay. So f plus g of x is just kind of a funky function notation. It's the same thing as if I wrote f of x plus g of x. So this notation mean the exact same thing. And all it means is what is f of x? 2x plus 1. What's g of x? You just take them and add them together. So combine like terms. What do we get?
3x
3x
minus 2.
minus 2. Okay, does that make sense? Yeah? Yeah? Okay. All right, so everyone, you get 10 seconds to discuss f minus g.
I got 4. X plus 4.
No, are you okay?
Oh, you're fine. But this is like an equation for like, it'd be easy to
All right, if I write f of x minus g of x, what do I have to put g in? Parentheses, because I got to make sure I subtract the whole function, not just the first term. Really important, you subtract the whole thing, right? So, what's 2x minus x? X. What's 1 minus negative 3?
Plus 4.
Plus 4. Very good. Is that okay? Yeah? Okay. All right. What do you think this means to do? Multiply. This is f times g. What do you think we're going to have to do to multiply these together?
multiply by FOIL.
Not factor, it's already factored. FOIL or distribute, right? We're going to have to distribute it out. For time's sake, I'm going to just walk you through. So 2x squared minus 6x plus x minus 3. And then if we combine like terms, 2x squared minus 5x minus trace. Very good. All right, one more. We're done with this screen. We're almost done with everything. We've got a couple more little ones. All right, f divided by g. So this is f divided by g. F of x is 2x plus 1. G of x is x minus 3. Is there anything I can do to simplify that?
No.
Can I cancel these x's?
No.
Almost like you almost fell for it. Almost gotcha. No. You can only cancel common factors. Right? Okay, so no, that is it. You just like write it and walk away. Sophia, how you doing? Last concept and we're done for the day. Oh, I've lost you all. I know. It has been such a long week. Too long. All right.
Yeah, oh yeah.
That was so Oh wait, domain is like X. Yeah, I know. Oh, I think range is Y and domain is X. Oh
Domain is the set of all x values for which the function is defined. Range is the set of all y values that are mapped to an x value in the domain. Meaning that there's a point there. So the set of all x values for which the function is defined, what does defined mean? It means that if you plugged in that x, you would get out a y. There's a point on the graph. Now, when we are finding domain, like let's take a look at this graph. Domain is x values. You think left to right. Lowest x value to highest x value. On this graph, what is the lowest x value?
2.
x value? -2. What is the highest x value? 4.
No, 15.
Do you understand? Left to right.
Yeah.
Gentlemen, please. Okay? When we write domain, I'm just going to put a big D for domain. 2 ways to write it. You can either write it in what's called set notation, which is kind of a compound inequality, x's between -2 and 4. Or, does anyone remember what this is called?
Function.
We learned it.
Interval notation.
I would not.
Okay? So, -2 to 4. Don't pack up. I want to keep you for a second. Range. What is the lowest y value on this graph? 0. What's the highest y value?
3.
3. All right? I've got you for one more minute. We're going to use it. I'm going to skip to the next page. I want to show you this one because this is a good one. Letter A. Let's see if I can get you. What's the domain?
Domain is infinite.
Negative infinity
To positive.
to positive infinity. Because our x's are going to keep going forever, to the left and to the right. What's the lowest y value? Hey, what's the highest y value? -3. All right, you can leave. Have a wonderful weekend. Remember, you have projects and bookwork. Okay, just for the recording, I'm going to go back and do the rest of these domains and ranges just so you can see examples. So the domain of, I'm going to write all my answers in interval notation just because it's faster. So think lowest x value to highest x value. The lowest x value is -6. The highest x value is 5. Then lowest y value, go bottom to top, -2. And then the highest y value is 4. So for x, you're going left to right. For domain, you're going left to right. And for range, you're going low to high. All right, let's go to the next screen. One of the things I didn't point out in class is you never put a bracket around infinity. You can't include infinity. It's not even a number. It's a concept. So you just have to put a parenthesis. For this one, when you're doing the domain, you just have to list the x values. 3, 2, -3, 1. And the range, 8, 7. You don't have to list the 8 twice. You just list it once for each time for all of them. Okay. For this guy, again, you're just listing 1, 2, 3. And for range, -3 and 8. Okay, almost done. Down here, lowest x value, you're going left to right, 0 to 3. Range, y values, low to high, 0 to 3. Domain, -2 to 3, left to right. Range, -2 to 2. We're going low to high. And this last one is going to hit every single x value and every single y value. Whew! That's the end, guys.